So guys, in this year's title, you're being asked to investigate how the rate of a chemical reaction can be controlled. So you need to choose a suitable reaction, you need to change one factor that affects the rate of that reaction, collect your data, analyse its properties, and then link the findings to the real world. So in areas like sustainability, health, technology, it's about showing that you understand reactions and how chemists control them. This question needs to be extremely specific. That's going to be very important for every single student. So it needs to clearly state what you're changing, what you're measuring, and sometimes conditions, so things like temperature, etc. So if someone cannot clearly see, for example, the independent variable, the dependent variable from your question, then it's too vague. So to come up with your research question, which is probably going to be the most challenging part of this, you need to start with a reaction that you already understand. And that's one piece of advice I can give you. Then ask yourself, what factors affect this reaction? Do we have things like concentration, temperature, surface area, catalysts? And then you want to phrase your question very clearly. So the structure I suggest for you is, how does X affect Y in this reaction? Some areas that you can investigate this year, they've made it very broad for us, are things like acid-base reactions, redox reactions, so they're all your titrations in both of those, decomposition, corrosion, electrochemical cells, that's linking into your electrochemistry, your oxidation reduction again, catalysts coming into rate of reaction, and even battery chemistry. So choose something safe and suitable for a lab, and also remember that you are expected to carry out this investigation in a 2-hour period, so it can't be something that is too lengthy in terms of the investigation process. So a question that we get asked a lot is, can students investigate the same title? And yes, of course you can, but your projects cannot be identical. So you must vary something like the factors tested, maybe one of you varies concentration and the other one varies temperature, or even just varies concentration to different degrees. Your method could be different, or even the thing that you're measuring, your measurement approach could be different. So everything must be your own work, and we have to be able to individually authenticate your work. So you can absolutely help each other out in the lab. You can carry out very similar reactions, but your factors should be different, and ultimately the work produced is individual. In the introduction research section, what we want to see, or what teachers will expect to see, is that you are clear, you are focused, and it's relevant. So include things like your research question, a strong hypothesis, relevant chemistry theory, proper referencing, don't copy and paste. Explain the chemistry in your own words. We want to see your understanding. So what a hypothesis is a question that I get asked almost every day as a teacher of chemistry, and have been asked for the past 13 years. A hypothesis is not a guess. So students have this misinterpretation that a hypothesis is, I guess what is going to happen. It's not. It is a prediction based on chemistry theory. So it explains what you expect to happen and why you expect that to happen, all based on chemistry theory that you've been learning in school over the number of months before your project. So to understand what theory you want to include, you want to think about things that directly explain your variable. So for example, collision theory might explain your rates of reaction, activation energies, redox principles in electrochemistry. If it doesn't explain your prediction, leave it out. So you don't want to get into a situation where you're just rambling off loads of different theories that are not actually relevant to the investigation you're carrying out. So how much theory is too much? As I've said in other questions, if it doesn't link directly to your investigation, leave it out. It's too much. Depth is better than length. So you want to show clear understanding of a good, strong theory than a vague understanding of multiple theories. You want clear explanation because that beats a long description. When you want to start doing your research for your project, you could start with your textbook that you're using in school, then use reliable scientific websites or educational sources. You can use the internet, you can use AI, you can use all of these things. But the important part of it is to keep a record of all your references. And remember, everything must be acknowledged properly. So if you use a website, if you use a book, if you use Google Scholar, AI, no matter what it is, you need to make sure you're keeping a log of that reference. In order to reference things properly, you need to make sure that you acknowledge books, websites, articles, and even AI tools. There is no problem using any of these things, but failure to reference is considered plagiarism. So you have to be honest and transparent. Maybe keep yourself a reference log throughout the process so that you're not trying to scramble at the end to find out where you actually got this information from. In your design and planning section, you want to clearly identify your variables. So your independent variable, your dependent variable, and your controlled variables. And then include things like a really detailed method, safety. Safety is going to be very important here. Equipment choice and why did you choose that equipment? And then how you ensure that it's a fair test. This section shows that you can actually think like a scientist if we were to bring you into a larger lab. To show research influenced design, you need to explain your decision. So every decision that you make with regard to equipment, etc., you need to tell us why you made that decision. So why those concentrations? Why that temperature range? Why that measurement method? Show your design came from your research. So you're trying to link this stage back to the research, the background research that you've already done previously. The difference between a controlled variable and a constant condition is that a controlled variable is something you deliberately keep the same. A constant condition is more of an environmental factor that stays stable but still needs to be acknowledged. So you're not consciously keeping it the same, it is going to remain the same regardless. In order to improve accuracy, you want to use precise equipment, repeat your trials, control variables very carefully, keep your method consistent. So consistency will be key for that part. And then accuracy comes from attention to detail. So every single movement that you're making in your method, in your process, why are you doing that? Take your time, be very deliberate in everything that you're doing. Repeat trials are very important for accuracy. They're one of the easiest ways for us to improve accuracy. The more times we repeat something, the more accurate the data becomes. So I would suggest a minimum of 3 per condition. So if you're changing temperature, you want to make sure you test that 3 times. That allows you to calculate averages and then improves your reliability. So how detailed do we need the method in this project? And it has to be detailed enough that another student could repeat it exactly. So if another student was to read your method, they should be able to follow it step by step and get the exact same results that you've gotten. You want to include things like units, precisions, clear steps, and safety. So in order to justify our equipment, that means that we're explaining why you chose the equipment that you did. So for example, I used a 0.01 gram balance to improve precision. So why did you specifically use that piece of equipment? Or something like, I've used a pipette instead of a graduated cylinder to improve accuracy. So explaining why you've chosen the equipment, that also improves your reliability. So safety is going to be very important in all of your investigations, and to conduct your experiment safely, you want to identify hazards. So that's like doing a risk assessment before you carry out the experiment. State clear precautions. So for every hazard that you identify, how are you going to reduce that hazard? How are you going to reduce the risk? Follow general lab rules that your school has laid out for you and carry out the experiment under teacher supervision. That is really important. It's also a recommendation that we shouldn't have any more than 8 experiments happening in a lab at one time. Time restraints may not allow for that, but it's certainly a good rule of thumb to try and follow. One of the most important sections of this project is going to be data and data analysis. So what do we want to include in there? We want clear tables of data. We want correct units. We need to know what you're actually measuring. Repeated trials. So try and do a minimum of 3 per variable, and then calculated averages, because that improves your reliability. Then what you want to do for your data analysis is show us graphs, trends, and scientific explanations. Don't just say it increased or it decreased. Tell us why that happened. Looking at uncertainties and significant figures is an important part again. So uncertainties show measurement precision. Significant figures show you understand accuracy. So they demonstrate what we call scientific maturity. So what you want to do is match decimal places to your measurement instrument. So if your measurement instrument is to 2 decimal places, you want to make sure your data is to 2 decimal places. You want to keep consistency. So if you're measuring temperature and you're always going to 2 decimal places, then you need to do that for every measurement that you take. Show one sample calculation for your averages. So you don't need to show how you've calculated every average, but maybe show one of them, and then avoid over precision. So you don't need to give temperature correct to 4 decimal places, for example, and that would be over precision. What do we do in a situation where our results don't support the hypothesis that we laid out at the beginning? So that's okay. You need to just state it clearly, analyse why, and discuss possible errors. Honest evaluation will still earn very high marks. The whole idea of this project is that it is about the process of the project. It is not about a product at the end. So when we work in a lab, we are not in a situation where we're going to get a perfect product every time. We have to make many mistakes, and many experiments don't work out. More often than not, they don't work out. But the process and your ability to then look back and reflect on that process is what the marks are going for with this project. When we look at meaningful improvement, it must address a real weakness in your project. So a good example would be use a water bath to keep a constant temperature. You don't want to avoid situations where you're saying something like, be more careful. That's too vague. Tell us why. Tell us how. How are you going to be more precise? How are you going to be more careful? In order to draw a proper graph, you need to make sure that you label both axes. You include units. Units are very important, and I say that through many parts of this. Choose a clear scale. So are we going up in 2s, 5s, 10s, 20s, 100s? Plot accurately as you can, at a suitable trend line if possible. So if you can clearly see that we have an increase, or we can clearly see a rate of reaction, add that in. Your graph should support your conclusion. So if your graph says that something, for example, is increasing, your conclusion should say the same thing. Section 6 of our project is where we put our conclusions. So you want to answer your research question directly. So you're going right back to the beginning. What was your research question? And we want to answer that. You want to state whether your hypothesis is supported or not, but you base all of this only on your data. Remember, if your hypothesis is not supported, if it hasn't worked out as you expected it would, that's okay. Your ability to recognize that from your data is what your marks are for. Always remember, process, not product. These projects are a great way for us to link chemistry with society in general and the impact that small decisions make on society. So you want to discuss here environmental impacts, industrial applications, sustainability, health, technology, and explain why your findings matter in the greater context. An area that we can look at is 4.3, which is our chemical environment. There's an awful lot of information in that section of the syllabus to be able to link our projects to. So take a look at that for some inspiration. Our real world links need to be detailed enough to show a real understanding. So not just a description, you want to have an analysis. So this is part of scientific literacy. Something that I recommend and I do with my own students is every time we do a small experiment in the lab, we have a discussion around how does this link to real world? Does it link to pharmaceuticals? Is it linked to plastics, materials, electrochemistry? Where is this used on a larger scale in the real world? So that practice over your 5th year and early parts of 6th year could help you to make those real world links much easier. So students ask us all the time as teachers, where am I going to lose my marks? And the reality is we're not correcting it for you. This is an SEC document and we don't have a marking scheme. We do have a marking rubric. The general area where students lose marks in report writing across the board is poor graphs, missing units, Weak evaluation, so weak ability to look back on the experiment and tell us why it did or did not work and why. Too much irrelevant theory, so if the theory is not relevant to your experiment, leave it out. Exceeding your word count, you only have 1,500 words in this project, so be careful of that. And then ignoring formatting rules. So there's very specific formatting rules laid out by the SEC, so make sure you're very well adept on those before you submit it. And precision matters. Be very deliberate in every decision you make around this experiment and be precise with your findings and your calculations. Do the words in your tables count towards your word count? And the answer is no. Words in tables, references, equations, and labels do not count towards your 1,500 word limit. It's a small word limit, and that's why we keep saying that precision is very important. So in order to keep within our word limit of 1,500 words, we're going to have to avoid waffle and irrelevant material. And to do that, you need to be focused. You need to link everything back to your research question. If it doesn't link to that question, leave it out. Be clear, be concise, use scientific language, and skillful brevity is what is going to earn marks here. So you want to try and limit over production of the same sentence again and again and again. So once you've said it, move on to the next part. So the very best of luck to everybody sitting Leaving Cert 2027. It is the first year for us to take part in this chemistry and practice investigation. It's a very exciting time for chemistry students across the country. So the best of luck with it. And always remember, this project is about the process, not the product.